All right, we are on our last lesson of our energy unit. So, in this unit, we have talked about so many forms of energy. So, we started out the unit talking about the different types of energies. In lesson 2, we talked about how energy can change from one form to another. And then, starting in lesson 3, we jumped into all the different forms of energy. So, we have talked about mechanical energy, which is the sum of kinetic and potential energy that an object has. We know that kinetic energy is moving energy. We know that potential energy is stored energy. Then from there, we looked at sound energy. We have looked at light energy. We have looked at electromagnetic energy in the form of electromagnetic waves. And then we focused on waves for a few days. We have also talked about heat and temperature, thermal energy. We did talk about initially in the unit that chemical energy and nuclear energy are going to come when we get into matter. So we have just done a deep dive into all the different forms of energy, and we're finishing with specific heat capacity. Which seems to be intimidating to a lot of students, but it's not really. So we're going to just get to the essential part of this, get the facts, get straight to the point, and then we're going to work out some word problems associated with this. So it's not rocket science to know that or realize that some things heat up faster than others and some things cool down faster than others. And that is when we're talking about how fast something heats up or how slowly something heats up, we are referring to the specific heat capacity of an object. So typically land heats up and cools down a lot faster than water because they have different specific heat capacities. So what is specific heat capacity? Well, be sure to write this in your notes. Specific heat is the amount of heat that's required to raise the temperature of 1 kilogram of a material by 1 degree Celsius. So specific heat of water is 4,184 joules for every kilogram times degree Celsius, whereas the specific heat of sand is a lot less. So earlier we said that land tends to heat up and cool down faster than water. Well, this is why, because it takes a lot more heat energy for the temperature of water to change by even 1 degree Celsius. So I have a question for you. I want you to look at the illustration at the bottom of the screen to answer the question. So how do you think the specific heat of a metal compares to the specific heat of air based on what you see in the picture? So pause the video now and answer this question. So one of the things I want you to notice about this illustration is the metal contains particles that are tightly packed, whereas the air is going to contain molecules that are more spread out. So if we're talking about specific heat, the specific heat of a metal is going to be a lot lower than the specific heat of air. And the reason for this is because it's not going to require a whole lot of heat energy to increase the temperature of a metal. Metals tend to increase their temperature and decrease their temperature very quickly, very easily. So the specific heat for metals are much lower than that of liquids or even gases such as air. So if I want to calculate specific heat, I can do that. And there's a formula. Now, I don't want you to be scared by this formula. It looks incredibly intimidating, but it's real simple. So once you know what these letters stand for, it's just really a plug and go type formula, just like we have been doing all along in physics. So the Q in this formula represents a change in thermal energy. Remember, the unit for energy is joules, so we're going to use a capital J. The M in this formula stands for mass. Now, for these particular formulas, we're going to want our mass to be in kilograms. Then delta T is going to be the temperature change or the change in temperature of the object. So in order to find change in temperature, you are going to have to subtract final temperature minus initial temperature. So in some of our word problems, they'll give you the change in temperature, and that's great. You don't have to do anything. Just plug that change in temperature in for delta T. But in some cases, it will tell you in the word problem, the temperature of this object changed from 10 degrees Celsius to 5 degrees Celsius. And if that is the case, then you're going to have to do a little bit of subtraction work to figure out the change in temperature. But it's really easy. Final temperature minus initial temperature. And then the C stands for specific heat. Usually this is going to be given to you in the word problem or in the form of a chart. Or I could ask you to solve for specific heat. And in that case, you would have to rearrange the formula in order to solve for C. All right, so let's look at an example together. So I've got my formula, Q equals M times C times delta T. And I want to know how many joules of heat are needed to raise the temperature of a 10-gram piece of aluminum from 22 degrees Celsius to 55 degrees Celsius. And then it gives me the specific heat of aluminum. So I've got everything I need to work out this problem. I'm solving for heat energy, which is Q. So all I have to do is multiply mass times specific heat times change in temperature. So the mass in this problem is 10. The specific heat is 0.9. And then I've got to do some calculation on the change in temperature. So you always do final temperature minus initial temperature. So this is going to be 55 minus 22, which is going to give me 33 degrees. That I'm going to plug in for delta T. So when you multiply 10 times 33 times 0.9, you should get 297 joules. So I want you to pause the video and just make sure that you get 297 joules as your answer. All right, now I want you to try this example. So I'm going to read it through and then I want you to pause the video and work it out. So how much heat is lost when a 640 gram piece of copper cools from 375 degrees Celsius to 26 degrees Celsius? And then I give you the specific heat of copper, which you're going to need. So I do want to point out something. In some of these problems, you might get a negative answer. You need to know what that means. So if temperature drops or decreases, your heat, you're losing heat. So that's going to be a negative value. If your temperature increases, then you're gaining heat. So you're going to have a positive value for heat energy. So here, since our copper is cooling, we are going to get a negative answer. And that negative answer means nothing more than heat is being lost. So pause the video, work that out, and see what you get. All right, so when you work this out, you should get a pretty funky number. So negative 85,886 and 39 hundredths. Or you may have rounded to the nearest tenth, and in that case, you would get negative 85,886 and 4 tenths. So negative 85,886 decimal 39 if you're rounding to the nearest hundredth. And then, of course, my unit on the end of that is going to be joules. Anytime we're looking for heat energy, joules is our unit. All right, let's do one more together. So how many joules of heat are needed to raise the temperature of 12 grams of iron from 26 degrees Celsius to 56 degrees Celsius? And then I give you the specific heat of iron as 1.2 joules per gram times degrees Celsius. So pause the video now, work that out, and let's see what you get. Now in this one, you should have a positive answer, and it should be 432 joules. So 432 joules is what you should get when you multiply the mass, which is 12, times the change in temperature, which is 30, times 1.2. So 432 joules. All right, so that ends our last lesson in the unit. You are going to have a specific heat practice worksheet that you have to do, so hopefully your teacher has given you that. And I will see you in the next unit, which happens to be my most favorite. It's our chemistry unit.